Picture this, a force so powerful it bends light, crushes stars into oblivion, and warps the very fabric of reality itself. Gravity isn't just what keeps your feet on the ground. It's the universe's ultimate architect, sculptor, and destroyer. What if I told you there are places in the cosmos where gravity doesn't just pull, it devours, where time slows to a crawl, space twists into knots, and matter is shredded into cosmic confetti? Buckle up, because today we're diving into the darkest, most violent corners of the universe to uncover 50 facts about gravity's most extreme playgrounds. From black holes that gulp down entire stars to neutron stars so dense a single teaspoon would weigh 1 billion tons, we're about to reveal how gravity transforms the cosmos into a spectacle of terror and wonder. And trust me, by the end of this journey, you'll never look at the night sky the same way again, ready to confront the universe's most monstrous forces. Let's begin. Now, let's zoom in on the undisputed champions of cosmic destruction, black holes. These aren't just objects with strong gravity, they're gravity's ultimate victory over everything, even light itself. Imagine a place where the pull is so intense that once something crosses a point called the event horizon, there's no turning back. Not a single signal, not a glimmer of light, not even the fastest particles in the universe can escape. This boundary isn't just a line in space, it's the point of no return where gravity wins forever. And the warping of spacetime around a black hole. Picture a bowling ball sinking into a trampoline, but instead of fabric, it's the very structure of reality bending under the weight. The closer you get, the more time slows down and space stretches like taffy. Black holes don't just pull, they rewrite the rules of physics in their vicinity, turning the universe into their own twisted playground. If gravity is the universe's architect, black holes are its wrecking balls. Now, let's take a closer look at one of the most bizarre and terrifying effects of a black hole's gravity: spaghettification. Picture this, you're drifting toward a black hole, feet first. At first, everything seems normal, but as you get closer, something horrifying happens. The gravitational pull on your feet is exponentially stronger than the pull on your head because they're just a little closer to the black hole. This difference in force stretches you like a piece of taffy, thinning you out into a long, noodle-like strand. It's not just you, anything that falls in, whether a star, a planet, or even light, gets pulled apart in the same gruesome way. Think of it like stretching a glob of syrup between two fingers. The thinner it gets, the more it fractures until it snaps. That's the brutal reality of tidal forces near a black hole. And here's the kicker, this isn't some distant sci-fi scenario. Astronomers have actually observed stars being torn apart by black holes, their material stretched into luminous streams before vanishing forever. So next time you're cooking spaghetti, remember, somewhere out there, gravity is doing the same thing on a cosmic scale, turning entire objects into cosmic noodles. But spaghettification is just the beginning when it comes to black holes' terrifying power. Now, let's scale things up to the true monsters of the cosmos: supermassive black holes. These aren't your average black holes. Imagine taking 4 million suns and crushing them into a single point. That's Sagittarius, a star, the supermassive black hole lurking at the heart of our Milky Way. While stellar black holes form from collapsing stars, supermassive ones are cosmic giants with masses ranging from millions to billions of times our Sun. Their gravity is so overwhelming that they don't just warp space around them, they command entire galaxies. Every star, planet, and speck of dust in a galaxy orbits this invisible titan, held in place by its gravitational grasp. Think of it like a puppeteer pulling strings on a galactic scale. Without these gravitational anchors, galaxies would fly apart, their stars scattering into the void. And here's something wild: scientists believe supermassive black holes might actually shape how galaxies evolve over billions of years, influencing where stars form and how they move. So next time you look up at the night sky, remember, You're seeing a dance choreographed by the most powerful gravitational force in the universe. But supermassive black holes aren't the only gravitational predators out there. Let's turn our attention to the cosmic drifters, rogue black holes wandering unseen through the darkness of space. Unlike their supermassive cousins anchored at galaxy centers, these lone wolves were likely ejected during violent galactic collisions or the explosive deaths of massive stars. Picture this: a black hole with several times the sun's mass, completely invisible, drifting silently through interstellar space. Its gravitational pull is so strong it could warp the paths of nearby stars or planets without ever revealing itself directly. The terrifying part: a rogue black hole could slip right through our solar system without us even knowing, at least until its gravity started bending light from distant stars or tugging planets out of orbit. Scientists estimate there could be hundreds of millions of these nomads roaming the Milky Way, ghostly remnants of the universe's chaotic past. Some might even be primordial black holes, formed in the earliest moments after the Big Bang, lurking in the shadows for billions of years. While we haven't definitively spotted one yet, astronomers hunt for their subtle gravitational fingerprints, strange stellar motions, or unexplained microlensing events where a black hole's gravity briefly magnifies a star's light. If one ever got too close, its tidal forces could shred planets before swallowing them whole. So next time you gaze at the night sky, remember, somewhere out there, invisible gravitational monsters might be drifting closer than we think. And that brings us to another ripple in spacetime's fabric: gravitational waves, the cosmic echoes of black holes colliding. Now, let's dive into one of the most groundbreaking discoveries in modern astrophysics: gravitational waves. Imagine two black holes locked in a deadly dance, spiraling closer and closer until they finally collide. This isn't just a violent merger, it's an event so powerful it sends ripples through the very fabric of spacetime itself. These ripples, known as gravitational waves, stretch and squeeze space as they travel outward at the speed of light, carrying with them the echoes of the universe's most extreme events. What's truly mind-blowing is that we can actually detect these waves here on Earth, thanks to observatories like LIGO. The Laser Interferometer Gravitational Wave Observatory, scientists have captured the faint whispers of black holes merging billions of light-years away. The precision required is staggering. LIGO measures changes in distance smaller than 1/10,000th the width of a proton. When two black holes collide, the energy released is so immense it can briefly outshine every star in the observable universe combined. That's right, for a fraction of a second, a single merger can radiate more energy than all the light from all the galaxies in the cosmos. These collisions don't just teach us about black holes, they're testing Einstein's theory of general relativity in ways we never thought possible. Each detection is like opening a new window into the universe, revealing secrets about how gravity works in the most extreme environments. And the best part: this is just the beginning. With more advanced detectors on the horizon, we're on the verge of hearing even fainter cosmic whispers, perhaps even the echoes of the Big Bang itself. So the next time you feel the ground beneath your feet, remember, spacetime itself is constantly rippling with the aftershocks of distant black hole collisions, and we're finally learning how to listen. Speaking of extreme gravity, let's explore how it can warp time itself, because near a black hole, clocks don't tick the way they do here on Earth. Now, let's bend our minds around one of gravity's wildest effects: time dilation near black holes. Picture this: the closer you get to a black hole's immense gravitational pull, the slower time ticks for you compared to someone far away. It's like nature's ultimate slow-motion button. Remember that scene in Interstellar where the crew visits a planet orbiting a supermassive black hole? For every hour they spend there, years pass back on Earth. That's not just sci-fi, it's real physics. Einstein's theory of relativity tells us that gravity doesn't just warp space, it warps time too. Near a black hole, the gravitational field is so intense that time stretches to a crawl. If you could hover near the event horizon, watching the outside universe would be like hitting fast forward. Galaxies would age and stars would die in what feels like moments to you. This isn't just theoretical. Scientists have actually measured time dilation here on Earth. Clocks run slightly faster on mountaintops, where gravity is weaker than at sea level. But near a black hole, the effect is extreme. Imagine two astronauts. One orbits the black hole while the other stays far away. When they reunite, the orbiting astronaut might have aged minutes while the other has aged decades. It's a staggering thought. Gravity doesn't just shape where we are, but when we are. And while we might never get close enough to a black hole to experience this firsthand, the universe is full of these cosmic time warps, reminding us that time itself is far more fluid than our everyday experience suggests. Up next, we'll shift from the mind-bending to the mind-crushing, because neutron stars take gravity's extremes to a whole new level. Now, let's take a step into the realm of the unimaginably dense, where gravity doesn't just bend the rules, it shatters them. Neutron stars are the cosmic leftovers of massive stars that went supernova, and their gravity is so intense it defies common sense. Picture this: a single teaspoon of neutron star material wouldn't just be heavy, it would weigh billions of tons. To put that into perspective, that's like taking Mount Everest, crushing it down to the size of a sugar cube, and handing it to you on a spoon. The sheer density is mind-blowing. How does this happen? When a massive star collapses, its core gets squeezed so tightly by gravity that protons and electrons merge into neutrons, packing an entire star's worth of mass into a sphere no bigger than a city. The result, a neutron star's surface gravity is around 100 billion times stronger than Earth's. If you dropped a marshmallow from just 1 meter above its surface, it would hit with the energy of a nuclear bomb. That's not science fiction, it's the raw power of gravity taken to its extreme. And here's the wild part: neutron stars aren't just dense, they're also spinning. Some rotate hundreds of times per second, their gravity whipping their surfaces into perfect spheres despite the insane speeds. It's a reminder that in the universe's most extreme corners, gravity doesn't just shape matter, it redefines it. Up next, we'll see how these cosmic powerhouses turn their gravity into light, firing beams across the cosmos like interstellar lighthouses. But gravity doesn't just crush, it also creates. Now, let's talk about pulsars, the universe's ultimate cosmic lighthouses. These rapidly spinning neutron stars take their mind-bending gravity and turn it into something spectacular. Beams of radiation so intense they pierce through the darkness of space. Here's how it works. The neutron star's insane magnetic field, trillions of times stronger than Earth's, channels charged particles along its poles. As the star spins sometimes hundreds of times per second, these beams sweep across the cosmos like an interstellar spotlight. If Earth happens to lie in the path of that beam, we detect it as a pulse of radiation, hence the name pulsar. And here's what's truly wild: these pulses are ridiculously precise. Some pulsars keep time better than atomic clocks, with rotations so consistent they rival the most advanced human-made timekeepers. The Crab pulsar, for example, spins 30 times per second, and its rhythm hasn't wavered in nearly 1,000 years. That's gravity and magnetism working in perfect, terrifying harmony. But pulsars aren't just cosmic curiosities, they're also tools. Astronomers use their steady pulses to map the galaxy, test Einstein's theory of relativity, and even search for gravitational waves. So the next time you hear about a pulsar, remember, it's not just a dead star, it's a gravity-powered beacon shining a light on the universe's deepest mysteries. Up next, we'll meet the neutron star's even more volatile cousin, a magnetar, where gravity and magnetism team up to unleash cosmic chaos. Now, let's step into the realm of cosmic extremes where gravity and magnetism collide in the most violent way possible. Meet Magnetars, the neutron star's unruly sibling, armed with a magnetic field so powerful it defies imagination. These ultra-dense remnants of dead stars don't just have gravity strong enough to crush atoms, they're also wrapped in magnetic fields a quadrillion times stronger than Earth. To put that in perspective, if a magnetar sat halfway between Earth and the Moon, its magnetic pull would strip the data from every credit card on the planet. But here's where things get even wilder. That insane magnetism doesn't just sit quietly, it snaps. The crust of a magnetar, already under unimaginable gravitational pressure, occasionally cracks under the strain, triggering starquakes. These aren't your average tremors. A single magnetar starquake releases more energy in a fraction of a second than our Sun does in 100,000 years. And when that happens, the magnetar unleashes a burst of gamma rays and X-rays so deadly it could sterilize entire planets light years away. In 2004, a magnetar flare from 50,000 light-years away actually disturbed Earth's upper atmosphere despite being halfway across the galaxy. What makes magnetars even more fascinating is their rarity. Of the billions of neutron stars in the Milky Way, only around 30 are confirmed magnetars. But when they act up, they steal the cosmic spotlight. Some scientists believe these violent outbursts might even be the source of mysterious deep space signals like fast radio bursts. So while pulsars are the universe's precise timekeepers, magnetars are its unpredictable rebels, gravity and magnetism fused into a ticking time bomb. Next up, we'll explore another gravitational heavyweight, white dwarfs, where dying stars defy collapse in a spectacular last stand. Now, let's shift our gaze to another cosmic heavyweight, white dwarfs, the glowing embers of stars that refuse to fade quietly. When a star like our Sun exhausts its nuclear fuel, it doesn't just vanish. Instead, it sheds its outer layers in a dazzling planetary nebula, leaving behind a dense, Earth-sized core, the white dwarf. But don't let its small size fool you. Packing nearly half the mass of the Sun into a sphere no bigger than Earth, a white dwarf's gravity is so intense it warps the very fabric of matter. Here's the mind-bending part. Under this crushing gravitational force, atoms don't just get squeezed, they're utterly dismantled. Electrons are ripped from their orbits, and what remains is a bizarre quantum soup called electron-degenerate matter. Imagine compressing a car into the size of a sugar cube, then cranking the pressure up 1,000,000 times. That's the level of density we're talking about. A single teaspoon of white dwarf material would weigh as much as an elephant here on Earth. But gravity's grip on a white dwarf isn't infinite. These stellar remnants cling to existence thanks to a delicate balancing act. The outward pressure of those crushed electrons pushes back against gravity's relentless pull, creating a cosmic stalemate. This equilibrium is so precise that if you added just a bit more mass, say, by siphoning gas from a companion star, the white dwarf would cross a critical threshold and detonate in a cataclysmic supernova. White dwarfs may lack the flashy violence of magnetars or the inescapable pull of black holes, but they're proof that even in death, stars wield gravity like a sculptor's chisel, shaping matter into forms that defy earthly logic. Up next, we'll see what happens when you take a step onto one of these gravitational nightmares. Spoiler, it won't end well. Now, picture this. What if you could take a single step onto the surface of a white dwarf? The moment your foot touched down, the sheer force of gravity would hit you like a trillion-ton hammer. We're talking about a gravitational pull so extreme, it's hundreds of thousands of times stronger than what we experience on Earth. Your body wouldn't just buckle, it would be flattened into a layer thinner than paper in an instant. To put that into perspective, imagine the weight of 50 jumbo jets pressing down on every square inch of your body. That's the kind of crushing force we're dealing with. Even the bones in your legs, which can support your weight here on Earth, would shatter like glass under that pressure. Your entire body would collapse into a smeared-out puddle of atoms, stretched and compressed beyond recognition. And here's the wild part, this isn't some distant sci-fi scenario. If a white dwarf were to drift too close to our solar system, its gravity could wreak havoc on planets, ripping them apart before swallowing them whole. It's a chilling reminder that in the universe, gravity isn't just a force, it's a cosmic wrecking ball, reshaping matter in ways we can barely comprehend. But don't worry, white dwarfs may be deadly up close, but from a safe distance, they're some of the universe's most fascinating relics. Next up, we'll explore how gravity doesn't just destroy, it also binds stars together in dazzling cosmic dances. Now, let's shift our gaze to the cosmic ballet of binary star systems, where gravity doesn't just crush or distort, but orchestrates a breathtaking dance between two stars locked in an eternal embrace. Picture two massive stars, each with their own gravitational pull, whirling around a shared center of mass like partners in a celestial waltz. Their orbits can be so precise, they trace out elegant loops over centuries, bound together by the same invisible force that could tear a planet apart. But don't let the beauty fool you, this dance can turn deadly. When binary stars orbit too close, their gravitational tug-of-war can spiral into chaos. Imagine one star siphoning material from its companion, creating a swirling disk of superheated gas, or worse, a collision. When two stars finally crash, the explosion outshines entire galaxies for a brief, blinding moment. It's gravity's way of reminding us that even the most harmonious systems can erupt into violence. And here's the twist: binary systems aren't rare. In fact, most stars in the universe have a partner. Our sun might seem lonely, but out there, gravity prefers company. From serene, wide orbits to chaotic, close encounters, these duos show us how gravity shapes not just individual objects, but the very relationships between them. Up next, we'll meet the universe's runaway stars, once flung from their homes by gravity's ruthless hand. Now, let's turn our attention to one of gravity's most dramatic escape artists, hypervelocity stars. These aren't your average celestial wanderers. Imagine a star ripped from its home galaxy and hurled into the void at speeds topping millions of miles per hour. How? It's all thanks to the monstrous gravitational pull of a supermassive black hole lurking at the galaxy's heart. Picture this: a binary star system drifts too close to the black hole's grasp. One star gets captured while the other is slingshotted outward with unimaginable force like a cosmic catapult. The ejected star doesn't just drift away, it's flung so violently that it breaks free from the galaxy entirely, becoming a lone traveler in the intergalactic darkness. What's truly mind-blowing is the speed. Some hypervelocity stars race fast enough to cross the distance between Earth and the Moon in just minutes. And they're not rare anomalies. Astronomers have spotted dozens of these renegades streaking through space, their trajectories tracing back to violent encounters with black holes. But here's the twist: these stars aren't just runaway fugitives. They're cosmic breadcrumbs, helping scientists map the hidden gravitational forces of the universe. By tracking their paths, we can uncover secrets about the black holes that launched them, a proof that even in exile, these stars tell a story. Next up, we'll witness gravity's role in a far larger showdown: galactic cannibalism, where entire galaxies collide and merge under its unyielding grip. Now, let's zoom out to witness gravity's grandest spectacle: galactic cannibalism. This isn't just a cosmic collision, it's a slow-motion feast where larger galaxies devour smaller ones, all thanks to their overwhelming gravitational pull. Picture the Milky Way and Andromeda, two titans on a collision course. In about 4 billion years, their mutual gravity will drag them into a violent dance, twisting their shapes and merging them into a single, even larger galaxy. But how does this gravitational feast unfold? Imagine a smaller galaxy drifting too close to a massive neighbor. Like a spider caught in a web, the smaller galaxy gets stretched and torn apart by tidal forces, gravity's relentless tug-of-war. Stars, gas, and dust are ripped from their orbits, forming long, luminous streams called tidal tails. Over time, these remnants are absorbed, becoming part of the larger galaxy's structure. Here's the twist: this isn't destruction, it's cosmic recycling. The Milky Way itself bears the scars of past meals, with remnants of devoured dwarf galaxies still orbiting our galactic halo. Andromeda, our future merger partner, has an even more violent appetite. Studies suggest it's already consumed dozens of smaller galaxies. What's truly staggering is the scale. These mergers can take billions of years, with gravity orchestrating every step. Yet, despite the chaos, stars rarely collide. Space is so vast that they simply slip past one another like grains of sand in a hurricane. By studying these galactic mergers, astronomers unlock secrets about dark matter, galaxy evolution, and even the fate of our own cosmic neighborhood. Up next, we'll explore an invisible force shaping the universe itself, dark matter's gravitational grip. Now, let's peel back the curtain on one of the universe's greatest enigmas, dark matter's invisible grip. While we can't see it, touch it, or even detect it directly, its gravitational influence is everywhere, weaving the cosmic web that holds galaxies together. Imagine an unseen hand shaping the universe, its pull so strong that without it, galaxies would fly apart like spinning tops, losing their balance. Here's the puzzle. When astronomers measure the mass of galaxies based on visible stars and gas, the numbers don't add up. The outer edges of galaxies rotate far too quickly for the gravity of visible matter alone to hold them together. Something unseen, dark matter, must be providing the extra gravitational glue. In fact, dark matter outweighs ordinary matter by a staggering ratio of 5:1, making it the universe's dominant gravitational force. But how does this shadowy substance work? Picture a galaxy as a city, with dark matter as its vast, invisible infrastructure scaffolding that keeps everything from collapsing. Its gravity bends light around galaxies, a phenomenon called gravitational lensing, which lets us map its hidden presence. Even more mind-bending, dark matter's pull doesn't just bind galaxies, it dictates how they form in the first place, clumping into halos that attract gas and stars like cosmic magnets. Yet for all its power, dark matter remains a mystery. Is it a sea of exotic particles, a flaw in our understanding of gravity itself? Every observation deepens the intrigue, from the way galaxy clusters collide to the eerie voids where dark matter's absence leaves emptiness stretching for millions of light years. One thing's certain, without dark matter's gravitational grip, the universe as we know it wouldn't exist. Up next, we'll see how this invisible force bends light itself, revealing hidden corners of the cosmos through gravitational lensing. Now, let's turn our attention to one of gravity's most dazzling tricks, gravitational lensing. Picture this: a massive object like a galaxy or a black hole warps the fabric of spacetime around it so intensely that it bends light itself, just like a magnifying glass bends sunlight. This isn't science fiction, it's a real phenomenon predicted by Einstein's theory of relativity, and it's how we've uncovered some of the universe's best-kept secrets. Here's how it works. When light from a distant galaxy travels toward us, it doesn't always move in a straight line. If it passes near a massive object, the object's gravity acts like a cosmic lens, twisting and magnifying that light. The result, we might see multiple distorted images of the same galaxy, stretched into arcs or even a perfect ring, a so-called Einstein ring, around the foreground object. It's as if the universe handed us a natural telescope, revealing galaxies so far away they'd otherwise be invisible. But gravitational lensing isn't just for show. It's a powerful tool for astronomers. By studying how light bends, we can map the distribution of dark matter, since its gravity contributes to the lensing effect. We've even used it to spot some of the earliest galaxies in the universe, their light amplified by this cosmic quirk. And in one groundbreaking test, observations of lensing during a solar eclipse confirmed Einstein's prediction that gravity bends light, solidifying relativity as one of science's greatest triumphs. The real magic: lensing doesn't just reveal hidden objects, it lets us weigh the lens itself. By measuring how much the light bends, we can calculate the mass of the foreground galaxy or cluster, including the invisible dark matter lurking within. It's like cosmic detective work where gravity's fingerprints are written in the warped light of distant stars. Up next, we'll take a closer look at those stunning Einstein rings, rare, perfect circles of light that are among the most beautiful proof of relativity in action. Now imagine stumbling upon a perfect circle of light in the depths of space, a cosmic halo so precise it looks like it was drawn by the universe itself. These are Einstein rings, one of gravity's most breathtaking masterpieces. When a distant galaxy, a black hole, or even an entire cluster of galaxies aligns perfectly with Earth, their immense gravity bends the light from objects behind them into a flawless ring. It's like holding up a cosmic magnifying glass and seeing the distant universe wrapped around a glowing circle. What makes these rings so special? They're vanishingly rare. For an Einstein ring to form, the background light source, the massive foreground object, and our line of sight must align with near mathematical precision. Even a slight misalignment distorts the ring into arcs or smudges. But when conditions are just right, the result is a shimmering loop of light, a direct snapshot of spacetime itself being warped. But these rings aren't just celestial eye candy. They're gold mines for scientists. By studying their curvature, astronomers can measure the mass of the foreground object down to the tiniest detail, including the invisible dark matter that makes up most of its weight. Some rings even reveal multiple copies of the same background galaxy, like a funhouse mirror reflecting the cosmos. And in a few extraordinary cases, Einstein rings have helped us spot galaxies so ancient they existed when the universe was just a toddler. Here's the wildest part. These rings are proof that Einstein's math was eerily accurate. Long before telescopes could capture them, his equations predicted their existence. Today, every Einstein ring we find is like a cosmic stamp of approval on relativity, a reminder that even in the vast chaos of space, gravity follows rules so elegant they border on art. Up next, we'll explore how gravity's extreme forces power the brightest beacons in the universe, quasars, and why they outshine entire galaxies. Now, let's turn our attention to the universe's ultimate powerhouses, quasars. These dazzling cosmic beacons are so bright they can outshine entire galaxies, and it's all thanks to the extreme gravitational forces of supermassive black holes at their cores. Picture a black hole with the mass of billions of suns, greedily devouring everything around it. As gas, dust, and even stars spiral into its clutches, they don't just vanish quietly. Instead, they're heated to unimaginable temperatures, creating a swirling disk of supercharged plasma that blasts out enough light to travel across billions of light years. What makes quasars truly mind-blowing is their sheer scale. A single quasar can be thousands of times brighter than the Milky Way, yet it's all coming from a region no larger than our solar system. That's like squeezing the energy of 1 trillion suns into a tiny dot in space. And here's the kicker. Most quasars we see today are relics from the early universe when black holes feasted on vast amounts of material. Their light has taken so long to reach us that we're essentially peering back in time, witnessing the universe's most violent teenage years. But quasars aren't just cosmic show-offs. They serve as lighthouses for astronomers, piercing through the fog of time and space to reveal secrets about the universe's structure. Their light gets distorted by galaxies and dark matter along the way, helping us map the invisible scaffolding of the cosmos. Some quasars even have jets of particles shooting out at nearly the speed of light, carving paths through intergalactic space like cosmic blowtorches. And let's not forget, quasars are proof that black holes aren't just destructive monsters. They're also engines of creation, shaping galaxies and seeding the universe with energy. Without their gravity, these brilliant beacons wouldn't exist, and the night sky would lose some of its most spectacular fireworks. Up next, we'll dive into another terrifying display of gravity's power, tidal disruption events, where black holes rip stars apart in a dazzling cosmic spectacle. Now, imagine a star's worst nightmare: wandering too close to a black hole's gravitational grip. This is where tidal disruption events unfold, one of the most violent shows in the cosmos. When a star strays near a supermassive black hole, the difference in gravity between the star's near and far sides becomes so extreme that it stretches the star like taffy, pulling it apart in a process called spaghettification. But here's where it gets spectacular. The star doesn't just vanish quietly. As it's torn to shreds, its gas forms a swirling, superheated disk around the black hole, glowing brilliantly as it's devoured. These cosmic feasts can outshine an entire galaxy for weeks or even months, releasing as much energy as a supernova. Astronomers call these flares tidal disruption events, and they're like black holes turning up the volume on their destructive power. The star's material doesn't just fall straight in, some gets flung outward in jets moving at nearly the speed of light, while the rest spirals inward, heating up to millions of degrees and emitting X-rays and ultraviolet light. What's truly fascinating is that these events aren't just about destruction, they're also cosmic laboratories. By studying the light from these flares, scientists can measure the black hole's mass, spin, and even the star's composition before it was ripped apart. Some tidal disruptions even leave behind clues about how black holes grow over time as they gorge on stellar material. And here's a chilling thought: our own Milky Way has a supermassive black hole at its center. While it's relatively quiet now, it's entirely possible that, given enough time, a star could wander too close and meet this gruesome fate. But for now, we get to witness these dazzling displays from a safe distance, reminders of gravity's terrifying power to reshape the universe one star at a time. Up next, we'll explore how gravity fuels the universe's most energetic explosions, gamma-ray bursts, where neutron star collisions unleash unfathomable power. Now, let's turn our attention to the universe's most powerful explosions, gamma-ray bursts. These fleeting but unimaginably violent events pack more energy in a few seconds than our sun will emit in its entire lifetime. And guess what? Gravity is the mastermind behind them. When two neutron stars, those ultra-dense remnants of dead stars, spiral toward each other, their immense gravitational pull accelerates the inevitable. As they collide, the resulting shockwaves unleash jets of radiation moving at nearly the speed of light, visible across the cosmos as a gamma-ray burst. But here's where gravity's role gets even wilder. The merger doesn't just create a blinding flash, it also forges heavy elements like gold and platinum in its aftermath. That's right, the gravitational chaos of a neutron star collision is essentially a cosmic gold factory. Scientists detected this firsthand in 2017 when gravitational waves from such a merger reached Earth, followed by a gamma-ray burst and a glowing kilonova, a multi-messenger event that confirmed decades of theory. What makes these bursts so terrifyingly efficient? It's gravity's ability to focus energy into narrow, hyper-energetic jets. If one of these jets were pointed at Earth from nearby, even thousands of light years away, it could strip our ozone layer and trigger mass extinctions. Thankfully, most gamma-ray bursts occur in distant galaxies, but they serve as a stark reminder of gravity's capacity for both creation and destruction on a cosmic scale. Up next, we'll unravel the mystery of the Great Attractor, a gravitational anomaly so powerful it's pulling entire galaxies, including our own, toward it. Now, let's journey into one of the universe's most baffling gravitational puzzles, the Great Attractor. Hidden behind the dense stars and dust of our own Milky Way, this colossal mystery exerts a gravitational pull so immense that it's dragging thousands of galaxies, including ours, toward it at speeds of over 14 million miles per hour. Imagine an invisible hand in the cosmos tugging entire galaxies like beads on a string. What makes the Great Attractor so enigmatic? For decades, its true nature remained obscured because our view of it is blocked by the Milky Way's galactic plane. But thanks to infrared and radio telescopes piercing through the cosmic fog, scientists have glimpsed clues. At its heart lies the Norma cluster, a massive gathering of galaxies, but even that doesn't fully explain the staggering gravitational force at work. Some theories suggest it's part of an even larger structure, like the Laniakea supercluster, a cosmic web where galaxies flow like rivers toward this gravitational sinkhole. Here's where it gets even stranger. The Great Attractor isn't the end of the story. Beyond it lies an even more massive pull, dubbed the Shapley Attractor, which might be the ultimate destination of this intergalactic current. Together, these forces reveal a startling truth. Gravity doesn't just shape galaxies, it choreographs their motion on scales so vast, it redefines our place in the universe. Up next, we'll venture into the eerie emptiness of cosmic voids, where gravity's absence creates deserts spanning hundreds of millions of light years. Now, let's step into the haunting silence of the cosmos, where gravity's grip loosens and emptiness reigns supreme. These are the cosmic voids, unimaginably vast deserts of space stretching hundreds of millions of light years, where galaxies are few and far between. Picture a universe with towering walls of galaxy clusters, and between them, these eerie, near-empty expanses where gravity's influence fades into nothingness. What creates these voids? They're the flip side of cosmic evolution. As gravity pulls matter into dense clusters and filaments, it leaves behind these sprawling gaps, some so large they could swallow thousands of Milky Ways without a trace. The Boötes void, one of the most famous, spans 330 million light-years and contains only a handful of galaxies. To put that in perspective, if our galaxy were placed inside it, the nearest neighbor would be so distant, the night sky would appear almost completely black. But don't mistake emptiness for inactivity. These voids play a crucial role in shaping the universe. Their lack of gravitational pull allows scientists to map the invisible scaffolding of dark matter, revealing how it bends light around their edges. They're also cosmic time capsules. Without dense matter to stir things up, the gas within voids remains pristine, offering clues about the universe's primordial state. And here's the twist: these voids aren't static, they're growing. As the universe expands, the gravitational tug of war between dense regions and these empty stretches accelerates, stretching the voids even wider. It's a reminder that gravity doesn't just create, it also carves, leaving behind these surreal landscapes of absence. Up next, we'll unravel how gravity weaves galaxies into the universe's grand tapestry, forming colossal threads known as galactic filaments. Now, let's zoom out and witness gravity's grand masterpiece, the galactic filaments. Imagine the universe as a cosmic spiderweb, with gravity as the invisible hand spinning threads of galaxies across unimaginable distances. These filaments are the universe's backbone, stretching hundreds of millions of light years and connecting clusters of galaxies like beads on a string. Here's how it works. After the Big Bang, tiny fluctuations in matter were amplified by gravity over billions of years. Denser regions pulled in more gas and dark matter, forming vast thread-like structures. Between them, the voids we just explored act like empty channels, framing this intricate web. The result: a cosmic network where galaxies align along these filaments, drawn together by gravity's relentless tug. The scale is staggering. The Sloan Great Wall, one of the largest known filaments, spans over 1,300,000,000 light-years. To put that in perspective, if you traveled at the speed of light, it would take you longer to cross this single structure than Earth has existed as a planet. And these filaments aren't just pretty cosmic decor, they're highways guiding galaxies toward dense clusters, where they'll eventually merge or orbit in giant celestial cities. But gravity's artistry doesn't stop there. Filaments also funnel gas into galaxies, fueling star birth and shaping their evolution. Without this delicate web, the universe would be a scattered, disorganized mess. Instead, gravity has woven a tapestry so precise that scientists use it to map dark matter, tracing the invisible threads that bind everything together. Up next, we'll confront a chilling possibility. What if gravity's grip becomes too strong and the universe itself collapses? The answer lies in a theory called the Big Crunch. Now, let's turn our gaze to one of gravity's most dramatic possibilities, the Big Crunch. Picture this: after billions of years of expansion, the universe's relentless growth slows, stops, and then reverses. Gravity, the silent architect of cosmic structures, could become the ultimate wrecking ball, pulling everything back into a single, unimaginably dense point, a singularity. Here's how it might unfold. Right now, the universe is expanding, with galaxies drifting apart like dots on an inflating balloon. But gravity is always tugging, trying to pull matter back together. If there's enough mass in the cosmos, more than we've currently observed, gravity could eventually overpower dark energy, the mysterious force driving expansion. The universe would hit a tipping point, like a ball thrown upward, finally succumbing to Earth's pull. As the collapse begins, galaxies would start racing toward one another, merging in violent collisions. Temperatures would skyrocket, stars would explode, and black holes would devour everything in their path. Space itself would shrink, cramming all matter into an increasingly smaller volume until crunch. The universe would end as it began, a hot, dense speck smaller than an atom. But here's the twist. Some theories suggest this singularity might trigger another Big Bang, birthing a brand new universe in an endless cycle of expansion and collapse. It's a cosmic reboot where gravity plays both destroyer and creator. Of course, this is just one possible fate. Current evidence suggests the universe is expanding faster, not slower, making the Big Crunch less likely. But gravity always keeps us guessing. Up next, we'll dive into the quantum realm, where gravity's rules get even stranger. Now, let's zoom in from the cosmic scale to the subatomic realm, where gravity's greatest mystery unfolds. Quantum gravity is the holy grail of physics, a theory that could finally bridge the gap between Einstein's general relativity, which governs the universe on large scales, and quantum mechanics, the bizarre rulebook for particles smaller than atoms. Here's the problem. General relativity paints gravity as the curvature of spacetime, a smooth fabric bent by mass. But quantum mechanics reveals a chaotic, pixelated world where particles pop in and out of existence. These two theories work flawlessly in their own domains, yet when combined, they clash spectacularly. Near a black hole's singularity, or in the first moments of the Big Bang, where both gravity and quantum effects dominate, our current physics breaks down entirely. Einstein spent his final decades chasing this elusive unification, but even he couldn't crack it. Today, physicists are exploring wild possibilities. String theory suggests tiny vibrating strings make up all matter, with gravity just another note in their cosmic symphony. Loop quantum gravity imagines spacetime as a network of woven threads. Then there's the holographic principle, proposing our three-dimensional universe might be a two-dimensional projection, like a cosmic shadow puppet show. The stakes couldn't be higher. Solving quantum gravity could reveal what happens inside black holes, how the universe truly began, or even whether alternate realities exist. It's a puzzle that reshapes not just physics, but our very understanding of reality. Up next, we'll explore a strange twist: primordial black holes, relics from the universe's birth that might be hiding in our cosmic backyard. Now, let's turn our attention to one of the universe's most intriguing what-ifs: primordial black holes. Unlike the monstrous black holes born from collapsing stars, these could be relics from the very first moments of the cosmos, forged in the chaos of the Big Bang itself. Imagine black holes no bigger than an atom, yet packing the mass of a mountain. If they exist, they might be drifting through space right now, invisible ghosts with gravity strong enough to warp their surroundings. Scientists speculate these tiny titans could be hiding in our solar system, their presence betrayed only by subtle gravitational tugs or flashes of Hawking radiation as they slowly evaporate. Some theories even suggest primordial black holes could explain dark matter, the invisible glue holding galaxies together. Picture this: a black hole smaller than a grapefruit, yet weighing as much as Earth, silently orbiting the Sun. It's a cosmic hide-and-seek game with stakes as high as rewriting physics. The hunt is on. Telescopes scan for telltale distortions in starlight, while underground detectors listen for the faint tremors of a microscopic black hole passing through Earth. If found, these ancient remnants could unlock secrets about the universe's birth, the nature of gravity, and even the fate of all things. Up next, we'll confront a fiery debate. Could black holes be surrounded by walls of flame, defying everything we thought we knew? Now let's dive into one of the most heated debates in modern physics: black hole firewalls. Picture this: you're falling toward a black hole, expecting to cross the event horizon smoothly, as Einstein's theory predicts. But what if, instead of an invisible boundary, you hit a raging wall of fire? That's the shocking idea. Some physicists propose a fiery curtain of high-energy particles lurking just inside the event horizon, ready to incinerate anything that dares to approach. This firewall hypothesis was born from a cosmic paradox. On one hand, quantum mechanics suggests information can't be destroyed, meaning whatever falls into a black hole must leave traces behind. On the other hand, Einstein's general relativity claims you'd feel nothing unusual at the event horizon. To reconcile these clashing theories, scientists proposed the firewall, a violent solution that sacrifices Einstein's smooth spacetime for quantum consistency. Imagine a black hole not as a gentle cosmic whirlpool, but as a monstrous furnace with a blistering edge. Critics argue firewalls defy the very principle of relativity, which states free-falling observers shouldn't notice anything strange at the event horizon. Supporters counter that quantum effects might rewrite the rules near these extreme gravitational zones. The debate is so intense it split the physics community, with some calling firewalls a necessary revolution and others dismissing them as a sign we're missing something fundamental. Could firewalls be real? If so, they'd force us to rethink black holes entirely, turning them from dark voids into cosmic infernos. The answer might lie in deeper theories of quantum gravity, a puzzle even Hawking wrestled with. Up next, we'll explore another gravitational mystery: echoes from black hole collisions that could whisper secrets about the fabric of spacetime itself. Now, let's turn our attention to another cosmic whisper: gravitational echoes. Imagine two black holes spiraling toward each other, merging in a violent dance that sends ripples through spacetime. But what if, after the initial burst of gravitational waves, there's something more? A faint, repeating signal, like an echo in a cavern, hinting at secrets hidden just beyond our current understanding. These hypothetical echoes could be the key to unlocking new physics. Scientists speculate that when black holes collide, their event horizons might not be as smooth as we once thought. Instead, they could have a quantum fuzziness or even a hidden structure like a cosmic hall of mirrors. As gravitational waves bounce off this mysterious boundary, they'd produce delayed echoes, subtle repetitions of the original signal. Detecting these echoes would be like hearing the universe's heartbeat twice, a clue that Einstein's theory of gravity might need an update. The idea challenges our classic view of black holes as simple, empty voids. If echoes exist, they'd suggest that event horizons are far more complex, possibly governed by quantum mechanics. Some theories even propose that these echoes could reveal the presence of a firewall or other exotic phenomena we've yet to imagine. So far, no definitive echoes have been found, but researchers are listening closely to data from observatories like LIGO and Virgo. Each new black hole merger is a chance to catch these ghostly signals. If we do, it could rewrite the rules of gravity, bridging the gap between Einstein's relativity and the quantum world. Up next, we'll venture into the realm of sci-fi turned science: wormholes, where extreme gravity might bend spacetime into tunnels across the cosmos. Now, let's take a leap from echoes to tunnels, wormholes, the cosmic shortcuts that have fueled science fiction for decades. But what if these fantastical passages aren't just the stuff of movies? Extreme gravity, the same force that crushes stars into black holes, might actually twist spacetime into bridges connecting distant corners of the universe. Picture a piece of paper folded in half with a pencil poking through. That's the basic idea. A wormhole would be that tunnel linking two separate points, turning a journey of billions of light years into a quick stroll. The math behind wormholes comes straight from Einstein's equations. Under the right conditions, gravity could warp spacetime so intensely that it forms a throat-like passage between two regions. But here's the catch: keeping a wormhole stable would require something called exotic matter, a hypothetical substance with negative energy that could prop open the tunnel against gravity's crushing grip. Without it, the wormhole would snap shut faster than you could say, Interstellar road trip. While we've yet to find evidence of natural wormholes, their possibility keeps physicists dreaming. Some theories suggest microscopic wormholes might flicker in and out of existence at the quantum level, far too tiny for us to notice. Others speculate that advanced civilizations, if they exist, could engineer them for travel. But even if wormholes are real, they'd come with risks. The intense gravity near their mouths could spaghettify anything passing through, and the exotic matter needed to stabilize them might be impossible to harness. Still, the idea captivates us because it challenges the limits of physics and imagination. Wormholes remind us that the universe's most extreme forces might hide the keys to its greatest mysteries. Up next, we'll push the boundaries even further. Could these gravitational twists in spacetime actually bend time itself? Now, let's venture into one of the most mind-bending possibilities of extreme gravity time travel. Imagine standing near the edge of a black hole, where spacetime isn't just warped but twisted into knots. According to Einstein's theory of relativity, this intense gravitational field could actually bend time itself, creating pathways to the past or future. One of the most compelling ideas is something called closed time-like curves. These are theoretical loops in spacetime where an object could travel forward in time, only to circle back to its own past. Picture a cosmic treadmill where time folds back on itself, allowing you to meet an earlier version of you. While it sounds like pure science fiction, the math behind it is shockingly real. Near a rapidly spinning black hole, gravity could drag spacetime around it so violently that these time loops might form. But before you start planning your trip to the dinosaur era, there's a catch. The energy and conditions required to create or sustain these curves are beyond anything we can imagine. You'd need a black hole spinning at nearly the speed of light, and even then, the tidal forces would likely rip apart anything attempting the journey. Plus, there's the infamous grandfather paradox. What happens if you travel back and accidentally prevent your own existence? Physicists debate whether the universe would somehow correct this, or if nature simply forbids such paradoxes altogether. Yet, the fact that gravity could twist time into these bizarre shapes reminds us how little we truly understand about the cosmos. It's a tantalizing glimpse into a universe where the rules we take for granted might just be suggestions. Next, we'll dive into an even stranger idea. What if our entire three-dimensional reality is just a holographic projection, shaped by gravity's deepest secrets? Now, let's stretch our imaginations even further with a concept that sounds like it's straight out of a sci-fi novel: the holographic principle. What if everything we see, touch, and experience in our three-dimensional universe is actually just a projection from a two-dimensional surface? At first glance, this idea seems absurd, but when you tie it to gravity, things start to make an eerie kind of sense. The holographic principle suggests that all the information in our universe, every star, planet, and even your thoughts, could be encoded on a distant, flat boundary, like a cosmic movie screen. Gravity, in this scenario, isn't just a force but a kind of illusion, emerging from the way this 2D data interacts. Think of it like a hologram on your credit card. The image appears three-dimensional, but it's actually stored on a flat, shiny surface. This wild idea comes from studying black holes, where gravity is at its most extreme. Scientists realized that the information swallowed by a black hole doesn't just vanish. It's smeared across its event horizon, the point of no return. That means the 3D chaos inside the black hole might be perfectly mirrored on its 2D surface. If that's true for black holes, could the entire universe work the same way? While it's still a theory, the holographic principle forces us to rethink reality itself. Maybe gravity isn't the fundamental force we thought it was, but a side effect of something deeper, written in code we're just beginning to decipher. And if that's the case, the universe is far stranger and far more elegant than we ever imagined. Up next, we'll explore how gravity doesn't just bend light and time. It can shatter entire stars, triggering explosions that outshine galaxies. Now, let's turn our attention to one of the most violent events in the cosmos: neutron star quakes. These aren't your average tremors. Imagine a star so dense that a single teaspoon of its material weighs billions of tons. Now, picture that star cracking under the strain of its own gravity, releasing energy equal to billions of nuclear bombs in a split second. That's the terrifying power of a neutron star quake. Neutron stars are the collapsed cores of massive stars that exploded as supernova. Packed tighter than anything else in the universe, their gravity is so intense that even their solid crusts made of ultra-dense atomic nuclei can't always hold together. When the crust fractures, it triggers a starquake, sending shock waves rippling through the star's interior. The energy released is mind-boggling. For context, the largest earthquake ever recorded on Earth released energy equivalent to about 50 megatons of TNT. A neutron starquake, try 100 trillion megatons. These quakes aren't just destructive, they're also cosmic gold mines for scientists. The vibrations they produce send out bursts of X-rays and gamma rays, giving us a peek into the star's internal structure. Some neutron stars, called magnetars, have magnetic fields trillions of times stronger than Earth's, making their quakes even more extreme. In 2004, a magnetar halfway across the galaxy unleashed a quake so powerful it briefly outshone the entire Milky Way. What's truly humbling is that these events are a reminder of gravity's raw, unrelenting power. Even the toughest materials in the universe can't escape its grip. And if you think that's intense, just wait until we explore how black holes don't just bend light. They cast shadows that reveal the very edge of spacetime itself. Now, let's step into the realm of one of gravity's most breathtaking illusions, the shadow of a black hole. In April 2019, humanity witnessed something unprecedented, the first ever image of a black hole's silhouette captured by the Event Horizon Telescope. This wasn't just a blurry smudge, it was a fiery ring of light, warped by gravity so extreme that it defies imagination. At the heart of this image lies the supermassive black hole in galaxy Messier 87, 55 million light-years away. What you're seeing isn't the black hole itself, since no light can escape it, but its shadow, a dark void encircled by a glowing halo. This ring is light from superheated gas swirling around the black hole, bent into a perfect loop by gravity's relentless pull. Einstein's theory of relativity predicted this exact phenomenon over a century ago, and here it was, staring back at us in vivid detail. The sheer scale of this achievement can't be overstated. The Event Horizon Telescope linked observatories across the globe, effectively creating a virtual telescope the size of Earth. Why? Because capturing a black hole's shadow requires resolving an object smaller than a grapefruit on the moon's surface from our vantage point. The precision needed is staggering, but what does this shadow really tell us? That fiery ring isn't just pretty, it's a cosmic measuring tape. Its size and shape confirm the black hole's mass, roughly 6.5 billion times that of our Sun, and offer clues about how it spins. Even more mind-bending, the light forming that ring isn't just bent. some of it orbits the black hole multiple times before escaping, creating a sort of gravitational hall of mirrors. This image isn't just a triumph of science, it's a visceral reminder of how gravity sculpts the universe in ways that still leave us awestruck. And if you think bending light is wild, just wait until we uncover how black holes might slowly evaporate, thanks to a bizarre quantum quirk named after one of history's greatest physicists. But here's where things get even stranger. Black holes aren't the eternal monsters we once thought. Thanks to a brilliant insight by Stephen Hawking, we now know these cosmic titans can actually fade away over time. Picture this: space isn't truly empty. Even in the darkest void, particles and their opposites, matter and antimatter, constantly flicker in and out of existence. Normally, they annihilate each other instantly, but near a black hole's event horizon, gravity's pull is so extreme that one particle might get sucked in while the other escapes. This escape act steals a tiny bit of the black hole's energy, causing it to lose mass over eons. Hawking calculated that the smaller the black hole, the faster it evaporates. A stellar mass black hole, it would take longer than the current age of the universe to vanish, but a tiny primordial one, poof, it could explode in a burst of energy in your lifetime. The irony is delicious. Black holes, the ultimate symbols of gravity's dominance, are undone by quantum mechanics, the rules governing the smallest particles. Hawking radiation bridges these two worlds, revealing gravity's limits in the face of the subatomic. And while we've never directly observed this evaporation, it's too faint for current telescopes. The math is rock solid. It's a humbling reminder that even the universe's most terrifying forces play by quantum rules. Now, imagine what happens when a black hole's mass shrinks to nothing. Does it leave behind a scar in spacetime or vanish without a trace? That mystery takes us straight to the edge of known physics, and perhaps to the next revolution in our understanding of gravity itself. But let's shift our gaze from the explosive end of black holes to the quiet yet equally dramatic fate of white dwarfs. These stellar remnants are the glowing embers of stars like our sun, but don't let their serene appearance fool you. Their destiny is ruled by a ruthless gravitational law known as the Chandrasekhar limit. Here's how it works. When a star exhausts its nuclear fuel, it sheds its outer layers, leaving behind a dense core, a white dwarf. Normally, the pressure of electrons pushing against each other keeps this core from collapsing further. But gravity is always lurking, waiting for its chance. If a white dwarf gains too much mass, say by siphoning material from a companion star, it crosses a critical threshold, 1.4 times the mass of our Sun. That's the Chandrasekhar limit, named after the astrophysicist Subrahmanyan Chandrasekhar, who cracked this cosmic code in the 1930s. Cross that limit and electron pressure crumbles under gravity's weight. The white dwarf implodes in a cataclysmic supernova, leaving behind either a neutron star or a black hole. It's a stellar balancing act, one where gravity decides whether a white dwarf fades quietly or goes out in a blaze of glory. And here's the twist: this limit isn't just a number, it's a universal checkpoint, a line in the sand drawn by gravity itself. Without it, we wouldn't have the elements that make up planets or even life. Every time you see a Type 1, a supernova lighting up the cosmos, remember, it's gravity playing its ultimate hand. Now, imagine if our Sun were destined to become a white dwarf. Lucky for us, it's too lightweight to ever hit that limit. But for stars that do, the Chandrasekhar limit is the final verdict, a reminder that even in death, gravity calls the shots. But while white dwarfs have their Chandrasekhar limit, neutron stars face an even more extreme gravitational showdown. Enter the Tolman-Oppenheimer-Volkoff limit, the ultimate breaking point where a neutron star's gravity becomes too powerful for even its own quantum forces to resist. Here's the cosmic tug-of-war at play. Neutron stars are already unimaginably dense, packing more than the Sun's mass into a city-sized sphere. Their cores are held up by neutron degeneracy pressure, a quantum effect where neutrons push back against collapse, much like electrons do in white dwarfs. But just like the Chandrasekhar limit, there's a threshold where gravity wins. For neutron stars, that critical mass is around 2 to 3 times the Sun's mass, though the exact number remains one of astrophysics' great puzzles. Cross this limit and the neutron star's fate is sealed. Gravity overwhelms neutron pressure, triggering a catastrophic collapse into a black hole. No supernova, no warning, just spacetime itself giving way under the weight of too much mass. This limit wasn't just dreamed up, it was calculated in the 1930s by physicists Richard Tolman, J. Robert Oppenheimer, and George Volkoff, who unraveled how quantum mechanics bends to gravity's will. What's fascinating is how this limit shapes the universe's most violent events. When two neutron stars merge, their combined mass often tips past the Tolman-Oppenheimer-Volkoff limit, birthing a black hole in a flash of gravitational waves and gamma rays. It's gravity's way of drawing another line in the sand, one that separates the universe's densest stars from its darkest voids. So next time you hear about a neutron star collision, remember, it's not just a cosmic crash. It's gravity, once again, proving it's the ultimate rule-maker in the universe's most extreme playground. Now, let's venture beyond our solar system to worlds where gravity takes on a whole new level of intensity. Picture a super-Earth, a planet several times more massive than our own, lurking in some distant star system. These colossal worlds don't just have stronger gravity, they wield it like a cosmic hammer. If you were to step onto the surface of a super-Earth with, say, 5 times Earth's mass, the experience would be brutal. Your body, evolved for Earth's gentle pull, would suddenly feel like it's carrying the weight of a car. Standing upright, forget it. Your bones would groan under the pressure and your muscles would fail in seconds. You'd collapse into a flattened, pancake-like mess, a grim reminder that gravity is anything but forgiving in the universe's heavier neighborhoods. But it's not just about crushing humans. Super-Earth gravity reshapes everything. Mountains couldn't soar as high as they do here. The planet's own weight would crush them down. Even the atmosphere would be denser and heavier, trapping heat and creating conditions more like a pressure cooker than a habitable world. Some of these planets might be rocky giants, while others could be shrouded in thick, toxic gases, their surfaces hidden beneath layers of crushing force. Here's the twist: some super-Earths might orbit in their star's habitable zone, where liquid water could exist, but could life survive there? It's a tantalizing question. Any organisms would need radically different biology, perhaps living in oceans beneath ice shields or floating in dense atmospheres. One thing's certain: gravity on these worlds doesn't just bend the rules, it snaps them in half. So while we search the cosmos for Earth-like planets, remember, the universe has a flair for extremes and gravity is always the artist. Next up, we'll explore the lonely wanderers of space rogue planets, where gravity is the only companion in the endless dark. Now, let's turn our attention to the cosmic drifters, rogue planets, the loners of the universe. These are worlds that don't orbit any star. Instead, they wander the endless void, untethered and alone, with nothing but their own gravity to keep them company. Imagine a planet flung from its home solar system by a violent gravitational encounter, perhaps a close call with a massive gas giant or a chaotic dance in a young star cluster. Once ejected, it becomes a nomad, drifting through interstellar space where temperatures plunge near absolute zero. No sunlight warms its surface, no dawn or dusk marks the passage of time. Just perpetual night, yet these rogue planets aren't entirely lifeless. Their gravity still holds sway. Some might retain thick atmospheres, trapping heat from their formation or radioactive decay deep inside. Others could have subsurface oceans kept liquid by tidal forces or geothermal energy, dark, hidden pockets where life, against all odds, might cling to existence. Here's something even wilder. Rogue planets might outnumber stars in our galaxy. billions of them could be lurking in the darkness, invisible to most telescopes because they emit no light of their own. Only when one passes in front of a distant star, bending its light with gravity, a phenomenon called microlensing, do we catch a fleeting glimpse of these ghostly worlds. So while they drift unseen, rogue planets remind us that gravity doesn't need a star to shape a world. It's a silent force sculpting the universe even in the deepest, loneliest corners of space. Next, we'll unravel one of gravity's most chaotic puzzles, the three-body problem, where predictability shatters under the weight of gravitational madness. Now let's dive into one of gravity's most perplexing puzzles, the three-body problem. Imagine trying to predict the exact movements of three celestial bodies like three stars or planets locked in a gravitational dance. Sounds simple, right? Think again. Unlike the predictable orbits of two objects, adding just one more turns the system into a swirling mess of chaos. Here's why. Gravity's pull between three objects creates an endless feedback loop of adjustments. Each body tugs on the others, altering their paths in ways that compound unpredictably over time. Tiny changes in starting positions or speeds can lead to wildly different outcomes, making long-term forecasts impossible. It's like trying to predict the path of a leaf in a hurricane. Every gust sends it spiraling in a new direction. This isn't just theoretical. Our solar system is full of three-body scenarios like the Sun, Earth, and Moon, but we rely on approximations because exact solutions don't exist. Even supercomputers can't crack the equations perfectly. The three-body problem reminds us that gravity, for all its power, has a mischievous side. It loves chaos. And here's the kicker: this chaos isn't just math. It shapes real cosmic events like stars flung from galaxies or planets ejected into darkness. Gravity's unpredictability is part of what makes the universe so thrillingly wild. Up next, we'll explore the Kármán line, where Earth's grip on gravity finally loosens and space begins. Now, let's rise above the chaos of the three-body problem and float toward a boundary that's both scientific and symbolic: the Kármán line. This invisible threshold, sitting 100 kilometers above Earth's surface, is where our planet's grip on gravity finally starts to fade and the vastness of space truly begins. Think of it as the cosmic welcome mat. Step beyond it, and you're officially an astronaut. But why 100 kilometers? It's not arbitrary. At this altitude, Earth's atmosphere becomes so thin that traditional aircraft can no longer rely on wings for lift. Instead, staying in motion requires reaching orbital velocity, speeds so high that you're essentially falling around the planet faster than gravity can pull you down. It's the ultimate balancing act between gravity's tug and the momentum of flight. Here's where it gets fascinating. The Kármán line isn't just a technicality. It's a legal and diplomatic frontier, recognized internationally as the boundary between airspace and outer space. Cross it, and you're no longer under any single nation's jurisdiction. You're in humanity's shared domain. Yet gravity hasn't fully let go. Even in orbit, astronauts still feel 90% of Earth's gravitational pull. True weightlessness comes from free-falling endlessly, a delicate dance with physics that makes space stations feel like they're floating. So the next time you gaze at the stars, remember, space isn't as far away as it seems. It's just a Kármán line away, a reminder that gravity's reach is both mighty and merciful, letting go just enough to let us explore the cosmos. Up next, we'll contrast this with the eerie absence of gravity, where the rules of the universe flip entirely. Now, let's take a step, or rather a float, into the opposite extreme. After exploring gravity's crushing dominance, imagine a world where it barely has a say at all. Welcome to the realm of zero gravity, or more accurately, microgravity. Here, the rules of physics you've known your entire life flip upside down literally. Picture this: an astronaut aboard the International Space Station, effortlessly gliding through the cabin, a pen hovering mid-air beside them. This isn't magic, it's microgravity in action. Contrary to popular belief, gravity isn't completely absent in orbit. Earth's pull is still at work, but the station and everything inside it are in a constant state of free fall, creating the illusion of weightlessness. It's like being on a roller coaster that never stops dropping except there's no track, just the endless curve of spacetime. But living in this floating paradise comes with quirks. Without gravity's steady hand, fluids don't behave as they should. Tears don't fall, they pool into shimmering bubbles on your eyes. Blood redistributes upward, giving astronauts puffy faces and spindly, bird legs as their bodies adapt. Even your spine stretches, adding an inch or two to your height until gravity reclaims you back on Earth. And it's not just the body that rebels. Simple tasks become puzzles. Eating, forget crumbs, they'll haunt your air vents. Sleeping, you'll need a strapped-in sleeping bag unless you fancy drifting into a colleague mid-snooze. Exercise isn't optional either. Without gravity's resistance, muscles and bones weaken alarmingly fast. That's why astronauts spend hours daily on treadmills and resistance machines, fighting microgravity's silent erosion. Yet for all its challenges, microgravity unlocks wonders. It's a laboratory like no other, where scientists grow perfect crystals, study flames that burn as cool spheres, and even experiment with printing human tissue in 3D, all impossible under Earth's stubborn gravity. Every mission teaches us more about thriving in this delicate balance, paving the way for future journeys to Mars and beyond. So while black holes remind us of gravity's terrifying might, microgravity shows its softer side, or rather, its absence. It's a reminder that the universe doesn't just bend under extreme force, it dances in the quiet spaces between. Next, we'll return to gravity's embrace, where the sun's pull weaves the solar system into its orderly tapestry. Now, let's turn our attention to the heart of our solar system, where gravity's invisible hand works its quiet magic. The sun may seem like a gentle giant from our vantage point, but its gravitational grip is the cosmic glue that binds every planet, moon, and asteroid in orbit. Without it, the solar system as we know it would simply unravel into chaos. Think of the sun as the ultimate puppeteer, with each planet tethered by an invisible string of gravity. The farther a planet is from the sun, the weaker that pull becomes, yet it's still strong enough to keep Neptune, nearly 3 billion miles away, steadily circling its fiery anchor. This delicate balance between gravity and motion is what keeps planets from spiraling into the sun or drifting off into the void. Even Pluto, now demoted to dwarf planet status, remains loyal to this gravitational dance, tracing its elongated path through the Kuiper belt. But the sun's influence doesn't stop at dictating orbits. Its gravity shapes the very rhythm of our cosmic neighborhood. Take Jupiter, for example. The gas giant's massive size could easily disrupt smaller planets, but the sun's steady pull keeps it in check, maintaining harmony among the inner worlds. Meanwhile, comets, those icy wanderers, are slung toward the inner solar system by the sun's gravity, putting on dazzling displays as they streak past Earth. And here's a mind-bending twist. The sun doesn't just pull on the planets, they pull back. Earth's gravity tugs ever so slightly on the sun, causing it to wobble in place. It's a tiny effect, but it's how astronomers detect distant exoplanets by spotting the subtle wobbles they induce in their own stars. So while black holes and neutron stars showcase gravity's extremes, the sun reminds us of its quiet, relentless consistency. It's the steady beat in the background of our cosmic symphony, a force so reliable we often take it for granted until we consider the chaos that would unfold without it. Next, we'll uncover the celestial parking spots where gravity's push and pull create perfect equilibrium, Lagrange points. Now, let's shift our gaze to one of gravity's most ingenious tricks, cosmic parking spots where forces perfectly cancel each other out. These are Lagrange points, the universe's way of offering celestial real estate where objects can hover effortlessly, held in place by a delicate gravitational ballet. Picture a tug of war between the Sun and a planet like Earth, where gravity's pull and the object's orbital motion strike a perfect balance. At these 5 special points, spacecraft can linger with minimal fuel, making them invaluable for astronomy and exploration. Take the James Webb Space Telescope, humanity's most powerful eye on the cosmos. It didn't just drift aimlessly into space, it was carefully parked at Lagrange Point 2, a million miles from Earth. Here, the combined gravity of our planet and the Sun keeps the telescope stable, with its sunshield perpetually angled to block heat and light. This vantage point lets Webb peer into the depths of the universe without Earth's glare or the Moon's interference, revolutionizing our view of distant galaxies and newborn stars. But Lagrange points aren't just for telescopes, they're cosmic way stations for future missions too. Imagine spacecraft refueling here before venturing deeper into the solar system, or asteroid miners using them as staging grounds. Even more intriguing, some Lagrange points collect space dust over time, creating natural traps for cosmic debris, hinting at where we might one day find floating caches of raw materials. What's truly mind-blowing is how these points defy intuition. At first glance, they seem like places where gravity should fling objects away, yet they're precisely where forces harmonize. It's as if the universe carved out these quiet corners for us to exploit, turning gravity from a relentless force into a willing collaborator. Next, we'll see how our moon's gentler but persistent tug shapes life on Earth in ways you might never expect. Now, let's turn our attention to a gravitational force much closer to home, one that's been shaping our world in silent, powerful ways for billions of years. The moon's gravity might seem gentle compared to black holes or neutron stars, but its effects on Earth are anything but subtle. Picture the ocean's tides rising and falling like clockwork. That rhythmic dance isn't just water moving. It's the moon's invisible hand tugging at our planet, stretching Earth's oceans toward it with every orbit. But the moon's influence goes far beyond tides. Over eons, its relentless pull has been slowing Earth's spin like a cosmic break. When dinosaurs roamed, a day was just 23 hours long. Thanks to the moon's gravity, our planet's rotation has been gradually winding down, adding milliseconds to each century. And this gravitational tango works both ways. Earth's tug is also pushing the moon away about 1.5 inches farther into space every year. Perhaps most astonishing is how the moon's gravity shaped Earth's very history. Without it, our axis would wobble wildly, triggering extreme climate swings that could have made life as we know it impossible. Instead, the moon acts as a stabilizer, keeping our planet's tilt steady and seasons predictable. Even the earliest life forms might owe their existence to the tides, which some scientists believe stirred the chemical soups that sparked life. So next time you gaze at the moon, remember it's not just a pretty face in the night sky. It's a gravitational architect quietly molding Earth's past, present, and future. And speaking of cosmic architects, wait until you hear how Jupiter's immense gravity acts as our solar system's ultimate shield. Now, let's zoom out from our lunar companion to meet the solar system's heavyweight champion, Jupiter. This gas giant isn't just a spectacle of swirling storms, it's Earth's silent guardian, wielding its immense gravity like a cosmic shield. Imagine Jupiter as a gravitational bouncer standing at the door of our inner solar system. When rogue comets or asteroids come hurtling toward us, Jupiter's pull often yanks them off course, flinging them away or even swallowing them whole. Scientists call this the Jupiter shield effect, and the numbers are staggering. Without Jupiter's influence, Earth would face asteroid impacts up to 1,000 times more frequently. Take the infamous Shoemaker-Levy 9 comet in 1994. Jupiter's gravity ripped it apart like tissue paper, absorbing 21 fiery fragments that could have been headed our way. Even smaller space rocks get diverted. Jupiter's gravity acts like a pinball bumper, redirecting debris into safer orbits or ejecting it from the solar system entirely. But here's the twist: Jupiter isn't always a hero. Its gravity can sometimes nudge objects toward us, like a clumsy giant accidentally knocking books off a shelf. Yet on balance, its protective role far outweighs the risks. Simulations show that without Jupiter, Earth might have endured extinction-level impacts every few 100,000 years, making advanced life nearly impossible. So while we marvel at Jupiter's storms and stripes, remember, its greatest gift is the quiet stability it provides, letting life on Earth thrive under its watchful pull. And speaking of cosmic stability, our next stop takes us to Saturn, where gravity weaves its magic into one of the universe's most stunning displays. Now let's turn our gaze toward Saturn, where gravity doesn't just pull, it sculpts. This ringed wonder isn't just a pretty face in the solar system, those dazzling rings. They're a masterpiece of gravitational artistry. Picture Saturn as a cosmic puppeteer, using its immense gravity to choreograph every glittering ice particle and dust speck in its orbit. But here's the twist: those pristine rings aren't as uniform as they seem. Gravity carves out gaps like the famous Cassini division, a dark band you could fit an entire fleet of planets into. How Saturn's moons play tug-of-war with the ring material. Take tiny Pan, a moon no bigger than a city. As it orbits, its gravity kicks debris out of its path, clearing a neat lane like a snowplow through a blizzard. And then there are the shepherd moons, celestial sheepdogs herding the rings into order. Moons like Prometheus and Pandora orbit just inside and outside the rings, their gravity nudging stray particles back into line. Without them, Saturn's rings would spread out into a messy haze over millions of years. Instead, they stay sharp and bright, a testament to gravity's invisible handiwork. But the real marvel: those rings are vanishing. Saturn's gravity is slowly pulling them inward, raining icy particles into the planet's atmosphere. In about 100 million years, this iconic feature could be gone, a fleeting spectacle in cosmic time. So while we admire Saturn's rings today, we're witnessing a delicate balance of creation and destruction, all orchestrated by gravity's relentless dance. And as we ponder the fate of Saturn's rings, our journey takes us even farther out to the solar system's shadowy frontier. Now, let's venture beyond the familiar planets and into the solar system's shadowy outskirts, where the sun's grip grows faint but never fully lets go. Here, in the frozen depths of space, lies the Oort cloud, a vast, mysterious shell of icy debris stretching nearly a light year from the sun. Think of it as the solar system's final frontier, a place where gravity's hold is so delicate that even the slightest nudge from a passing star could send one of its frozen inhabitants hurtling inward. This distant reservoir is home to trillions of comets, each a frozen relic from the solar system's birth. Unlike the orderly orbits of planets, these icy wanderers drift lazily, bound only by the sun's whisper-thin gravitational influence. It's a cosmic balancing act: too close, and they'd plunge toward the inner solar system; too far, and they'd escape into interstellar space forever. Occasionally, a gravitational nudge, perhaps from a nearby star or the Milky Way's tidal forces, dislodges one of these icy nomads, sending it on a million-year journey toward the sun. When that happens, we witness a dazzling comet, its tail glowing as it streaks through our skies. But for every comet we see, countless others remain in the Oort cloud's deep freeze, waiting for gravity's subtle push to set them in motion. What's truly mind-bending is the scale. The Oort cloud is so far away that Voyager 1, humanity's farthest-flung spacecraft, won't reach its inner edge for another 300 years. And yet, despite the distance, the sun's gravity still reigns supreme, a silent shepherd guarding the solar system's outermost flock. As we reflect on this distant, icy halo, we're reminded that gravity's influence knows no bounds. It shapes not just planets and stars, but the very edges of our cosmic neighborhood. And with that, our journey takes us even deeper into the universe's gravitational mysteries. But gravity isn't just a force that binds the cosmos, it's also a tool that clever engineers have harnessed to explore it. Picture this: a spacecraft too small to carry all the fuel it needs for a long journey gets a free boost from the very planets it's trying to study. This is the magic of gravity assist maneuvers, where a planet's gravitational pull becomes a cosmic slingshot, flinging probes across the solar system at breathtaking speeds. Here's how it works. As a spacecraft swings close to a planet, the planet's gravity tugs on it, accelerating the probe like a roller coaster gaining speed on a downhill slope. But unlike a roller coaster, the spacecraft doesn't just fall back. It steals a tiny bit of the planet's orbital energy, using it to catapult itself farther into space. The planet, massive as it is, barely notices the difference, but for the spacecraft, it's a game changer. Some of history's most iconic missions owe their success to this trick. Voyager 1 and 2 used gravity assists from Jupiter and Saturn to reach the outer planets and beyond. The Cassini probe relied on multiple flybys of Venus and Earth to reach Saturn, saving years of travel time and tons of fuel. Even the tiny New Horizons spacecraft, which raced past Pluto, got a crucial speed boost from Jupiter's gravity. What's truly brilliant is the precision involved. Engineers calculate these maneuvers down to the second, threading the needle between a planet's gravity well and the vastness of space. A slight miscalculation could send a probe hurtling off course, or worse, crashing into the planet itself. But when it works, it's a masterpiece of celestial mechanics, proving that sometimes the universe itself can be the best launch pad. So next time you gaze at the night sky, remember, the same force that keeps your feet on the ground is also the secret behind humanity's farthest voyages. And with that, we're ready to unravel another gravitational puzzle. Now, let's turn our attention to one of the most baffling gravitational mysteries in space exploration, the Pioneer anomaly. For decades, scientists were stumped by the strange behavior of the Pioneer 10 and 11 spacecraft. These intrepid probes, launched in the early 1970s to explore the outer solar system, began slowing down in ways that defied the laws of gravity as we understood them. Here's what happened. As the Pioneers journeyed beyond Saturn, mission controllers noticed something odd. Their speed was decreasing ever so slightly, as if an invisible hand was tugging them backward. The deceleration was tiny, about a billionth of the force we feel from Earth's gravity, but it was consistent and unexplainable. For years, this anomaly haunted physicists, sparking wild theories. Could it be evidence of unseen dark matter, a flaw in Einstein's theory of relativity? Or even a sign of new physics beyond our current understanding? The truth, as it often does, turned out to be far more mundane, but no less fascinating. After years of painstaking analysis, scientists traced the anomaly to an unexpected source: heat. The spacecraft's radioactive power generators emitted tiny amounts of thermal radiation, and as this heat radiated unevenly from the probes, it created a minuscule but measurable push against their direction of travel. In other words, the Pioneers were essentially slowing themselves down by glowing faintly into space. Yet the story doesn't end there. The Pioneer anomaly taught us a valuable lesson about the precision required in space exploration. Even the smallest, most overlooked details, like the warmth of a spacecraft, can have profound effects when dealing with the delicate dance of gravity and motion. It's a reminder that the universe still holds surprises, and sometimes the answers are hiding in plain sight. So while the mystery may be solved, the legacy of the Pioneers lives on, proving that even the quirks of gravity can lead us to deeper truths. And with that, we're ready to dive into our final frontier. Now, as we reach the edge of our cosmic journey, let's peer into the future where the next chapter of gravity research is already being written. Imagine a new era of discovery where scientists won't just observe the universe's most violent gravitational events, but listen to them with unparalleled clarity. That's the promise of missions like LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. This revolutionary observatory won't be bound by Earth's limits. Instead, it will float in space, forming a triangle of satellites separated by 2.5 million kilometers, each firing lasers to detect gravitational waves 1,000 times more sensitive than current instruments. Think of it like tuning a cosmic stethoscope to the heartbeat of colliding black holes and neutron stars, events so distant, their whispers are lost in the noise of our planet. LISA could uncover mergers from the universe's infancy, probe the warped spacetime around supermassive black holes, and even test Einstein's theories in ways we've never dared before. But it doesn't stop there. Other missions, like the Einstein telescope, aim to build underground detectors with sensitivity so sharp they might catch gravitational waves from the very first stars. What makes this future so thrilling isn't just the technology, it's the questions we'll finally answer. Are there hidden dimensions crumpling spacetime? Do tiny primordial black holes lurk in the dark? Could gravity itself have quantum secrets waiting to be cracked? Every ripple in spacetime LISA captures will be a clue, pulling us deeper into the mystery of how gravity shapes and shakes the cosmos. So while we've uncovered 50 astonishing facts about gravity's extremes today, the most mind-blowing revelations are still ahead. And when these missions launch, they won't just change textbooks, they'll redefine our place in the universe. Which of these future discoveries excites you the most? Drop your thoughts in the comments and don't forget to subscribe for more journeys into the unknown. The cosmos has only begun to share its secrets. From the crushing grip of black holes to the delicate dance of galaxies bound by invisible threads, gravity is the universe's ultimate sculptor, shaping reality in ways both breathtaking and brutal. We've journeyed through 50 astonishing facts, from stars torn apart by tidal forces to the eerie silence of cosmic voids where gravity's hand has never reached. We've seen how spacetime bends like rubber, how neutron stars defy density itself, and how dark matter's unseen pull weaves the cosmos together. Each revelation reminds us, gravity isn't just a force, it's the architect of existence, crafting everything from the tiniest atom to the grandest galactic web. So tell us, which fact left you awestruck? Was it the horror of spaghettification, the elegance of Einstein rings, or the mystery of the great attractor pulling thousands of galaxies toward the unknown? Drop your answer in the comments and let's geek out over the universe's extremes together. And if you're hungry for more cosmic wonders, hit that subscribe button and ring the notification bell, because the universe never runs out of secrets, and neither do we. Thanks for joining this gravitational odyssey. Until next time, keep looking up.